Wait, what? You took 310 in 6 second semester, right?
Actually, I took 310 over the summer.
Oh, okay, so that would apply.
Yeah.
I'm insane, but I don't hate myself that much.
No, but I do.
You know what? That's valid.
Yeah.
Carry on.
Top, right?
Yeah.
So, I really like it. The default make a lot of sense.
Not Tom.
Oh, okay.
This is Chrome OS.
Never mind, I hate it.
I do use Tom though on my home device. It has so much power. Tom's kind of stupid.
Yeah, like the main reason I play Pop is, well, one,
The workspaces.
have you tried i3? The workspaces and i3 kind of slow everything else away, but like the main reason I like Pop is one, it makes no not suck. Its defaults make so much sense. And two, there's no
The support is popular.
yeah.
More importantly, the biggest support with the workspace and the title. So like I'll have Chrome, terminal, Discord, workspace down, terminal, workspace down, Steam.
Yeah,
The game running in the corner.
Like I have, that's how I look at it. Well, pretty much
The Archman.
the Archman. I'm an Archman. Yeah, like I got workspaces too. And I got workspaces through my Polydor. I can get some on this.
So like, yeah, I don't know how your guys do it. A little bit of trolling. Just gonna bold what I say. And then I can't see the legs. No, I think my recruiter just kind of think that. She just sent it to me like on the phone. Right back to
Please sign across the name. Yes, I think people is trying to
visit.
Oh, yeah. That's great.
Absolute status. Back to typing, that's what I wanted to do. I wish I didn't have like crippling. So that's the right side of me. Not very tragic. Wi-Fi, couldn't stream this. That way, all I do is connect it. I get everything fully.
Who is she, Derek? Derek she.
It's a related like application when we did the services.
I told you, I think like going in is like, how can I instantly?
Ninad Kulkarni. No, you're not in trouble. I'm just randomly picking. I'm doing Monte Carlo search that we'll be talking about today. And I'm hoping that if I randomly pick some people and look at their faces, I might remember. Okay, I think it's 1:30. Right? Okay. And yeah, I know. Okay, so basically by the end of this class, I think the TAs are going to be releasing the problem set one. It would not be multiple choice. You will actually have to write the answers. But we will, I think to make it easy, I guess they said that they're just going to let you upload it for the grade scope. So you can basically scan what you have written and upload it. I think you've been doing this probably during this thing. So you don't have to bring the hard copy to the class. And then that apparently also makes the grader's life somewhat easier anyway. But I mean, you should just write with your handwriting. I mean, don't waste your time trying to type. Handwriting is fine. We have enough technology that you can take pretty good scans, even with a cell phone. Okay, that's that. And it's a problem. And actually, in some weird sense, I mean, I should have given the problem set earlier. We're actually kind of a little behind, but it'll be due 2 weeks from now, and it has everything until the end of A-star search. So the next one will then have some of this other stuff on game trees and so on. Okay. Yeah. And then I think the advantage of the online submission is that actually you can submit it to the end of the day, like 11:59 on the grade scope. So you don't actually have to be doing it in the class. So one less reason to miss the class because I'm doing homework. Okay. That's that. And other questions. So today, basically, I'm sort of going to get you to think of we actually wind up seriously expanding what you think about computation and decision making today. There are a whole bunch of new things that will be thrown at your thing before we then finally shift to MDPs and reinforcement learning. It's a very interesting transition today. So we were happily with a single agent, and then we allowed another agent whom the single agent is playing games with. And then we found that the moment there's another agent, the world is no longer static. It becomes dynamic. And so you don't get to say, let me first find the optimal solution and then start executing it, which is what A-star search was doing, right? If you have a bad heuristic, A-star search can take quite a long time before you can come up with the full solution, right? And the point is, I want to know, tell me something. Tell me what your move is. And even though the move part becomes very important in games, move part is also important in any dynamic scenario. Like if you're in the middle of the road and the trucks are coming at you, trying to figure out what would be my optimal policy of going from the middle of the road to getting an A+ in this course. And let me first figure out the optimal policy for the whole thing and then start executing it. I won't have any students left because you would be run over by the trucks. Do you understand what I'm saying? So you need to say that I need to do this I basically, right now, I have to make a decision while I think about and make a decision, commit to it. The moment you do the decision in the world, basically you are in a different state. Do you understand what I'm saying? And that brings up all sorts of interesting problems. The moment you make this decision, if you don't make this decision, you may be dead because the world is changing. Plus, you might be thrown out of the game because the game rules require that you make the decision. You make your move. But the moment you make your move, you may have unwittingly painted yourself into a corner. The people who paint themselves into a corner, they did so because they didn't do a star search. If they thought about exactly where do I want to be, in the evening I want to go to a party, right now I just have to complete this painting. If they figured out their entire plan for the whole day, they would have realized that painting themselves into a corner is a bad idea. They were just doing decisions with myopic decision making. That means very little look ahead. They're doing decisions. Because of which they found themselves painted themselves into a corner. Painting oneself into a corner is the nicer version of being run over by a truck. At least painting yourself into a corner, you can call your neighbor to, please rescue me, or maybe you just walk over the paint or something. Okay, but it's costly. But you can actually be dead because you made a mistake. So in general, today we'll start talking about this time pressure for decision making. In fact, we started talking about it last time because the reason we start thinking about depth-limited min-max is because there is no way you can look at the entire min-max tree to figure out what your first move is, because it'll take too long. Since you're only given a certain amount of time before which you have to make a decision, make a move, you need to find a way of, okay, this is going to be my move before I think more deeply. In fact, one of the things you may not have realized last time is that if you are thinking of something like this min-max tree, if you see the full tree, you know how to do min-max backup, alpha, beta pruning, etc. The depth-limited version essentially says, well, I'll just do like up to that depth. And then do min-max on this small a tree. So depth-limited min-max is like iterative deepening. You understand what I'm saying? Depth-limited min-max is like iterative deepening. The one difference is basically when you have this tree, these guys don't have obvious values. The terminal nodes have known values. Everybody agrees on the terminal nodes. This is a definite fill, this is a definite pass, this is a definite drop. The problem is in the middle of the chess, the board you can't tell how good is it for you. In fact, the difference between you and a grandmaster really is they can tell how good the middle position is, even though it's not. I mean, if you don't even know, if you, for example, are one of those people who continue playing after your king has been checkmated, you have no hope. Basically, you don't know the rules of the game. So you'll continue, just keep doing it. I mean, those guys are saying, no, you're done. No, I'm not done. I'll just keep doing it. Okay? But that, assuming that you understand the rules, at least everybody knows when they come to a terminal node of the game, understanding the game minimally means when you come to the terminal node of a game, you should know what the value is. But knowing what is the value of these middle states, it's a whole entire different thing. This is why we needed, in the iterative deepening depth first search, you just had to check whether the node is a goal node or not. Unlike IDDFS, you know that none of these guys are going to be, it's very unlikely that these are going to be terminal nodes, because you know that most of these trees are extremely deep. So you will have to assume that there is some heuristic evaluation function. Okay? And so you basically use those numbers. Maybe this is like 2, this is 7, this is 5. So your evaluation function said it's 2, this is, its goodness is 2, this guy's goodness is 7, this guy's goodness is 5. So you then, because you're the max guy, you will take max of these 2, 7, and 5. And then you will realize, right now, my move is this. Right? In life, you do this. You know, I don't know what's the best thing to do, but let me keep like a safety. This is my safety. This is my safe decision. If the clock says you have to make a decision now, I have one decision. But if I have some more time, then I will go one extra level. I will apply evaluation functions to this level. One of the other interesting things that's different from IDDFS is that at any given point of time, the tree has a fringe, because that's the last level of the tree that you have looked at. You only need to apply evaluation function to these nodes on the fringe. And then you just back it up min-max. Do you understand what I'm saying? Right? So it basically could happen that, so essentially I can make some other numbers here, you know, like totally different numbers. I'll just make up something. 17, 4, 9, 8, 2, and 15, 17. I just made these numbers up. Don't ask me where I got this evaluation function. Okay, if you know that game, you might make a reasonable heuristic evaluation function. Right? So now at this point, what will I do? I will say 17 and 4, this guy minimum is 4. 9, 8, 2, the minimum here is 2. And 15 and 17, the minimum here is 15. So now A again needs to decide what its best move is. Notice that this time it basically is going to pick between 4 and 2 and 15. So in fact, this is the better move. Did you see what I'm saying? As you think more, you keep changing your mind about what's the best move. Now, if the clock stops right now, that's the move you will make. You won't go back to the previous move. And if you have even more time, you go even deeper. If you have the maximum amount of time and it's like the smallest game, then at some point of time, you would have looked at the entire tree. There, you don't. All evaluation functions will have the property that if it's a guaranteed terminal node, they will take the real value of the terminal node. Just like heuristic functions, for goal, they must say 0. Otherwise, they are not admissible. Evaluation functions, there is no notion of admissibility per se, but essentially, they have to at least be minimally consistent. They have to say that the node, if the node is actually a terminal node, that everybody agrees is a terminal node, then I will take the value of that game at that point as the evaluation value. Only if I can't tell will I apply the rest of the evaluation function. Remember, that is why in the tic-tac-toe evaluation, I said, if it is a definite win for max, assume it is plus infinity, or a big plus number. If it is a definite loss for max, assume it is minus infinity, or a big negative number. If it is neither, then you count the number of rows, columns, diagonals open to the max, minus number of rows, columns, diagonals open to the min. That piece, this if, then, else, else, okay? So the last else part could have been applied any time, but you don't use it unless it's not a terminal node. That's the minimum thing you could do, because you definitely know that this is. Okay? So this is basically what is happening in the back of the depth-limited depth first search. And the reason you're doing this is you're essentially doing what I would call online decision making. That means you're making a decision as you're asked to make a decision. And if you have still some more time, think some more and can get a better decision. But the moment you execute the decision in the real world, you may not get to take it back. right? You know this even in chess, right? Basically, they'll hold this piece and dance in the air, but the moment it touches the board, by the rules of the game, that is a move. You can't just say, oh, my hand shook, that's not what I want. You're done. That's your move now. You're committed. If it turns out that that is a fatal move, and from there you can never recover, then you basically will you'll basically die, essentially, in chess, in any case. So it's very important to understand that online decision making is needed in the real world. And the online decision making is safe only if the world is ergodic. Remember I mentioned this ergodicity in the beginning of the class? Only if it is the case that you can always reach from any state of your world to any other state with non-zero probability. Right? Non-zero probability. Would you call it ergodic? And any state where there is death certainly is not ergodic. And even in an ergodic state, there can be inoptimalities. This is what you opened. This is the huge can of worms you opened when you said, I will do depth limited min-max. It looked like just a small extension. But you're suddenly now thinking in the world of online decision making. Another point about this is also in all the time in computer science up until now, you had, by the way, the last two guys in the row, in the very last row, you guys, unless you're seeing my slides, close the laptops or leave the class. It's the same for everybody. Do you understand what I'm just saying? So I'm not here to talk to the back of your laptops. Okay. So when you are essentially, these are the kinds of computations that are called anytime computations. Why? Because normally in computer science, if you have a program, you stop it in the middle, you get junk. You have to wait it until it terminates. You understand what I'm saying? Every program has to be allowed to, most normal programs that you've seen, most normal algorithms you have seen have the property that when they terminate, all the guarantees hold. Until they terminate, there's no guarantee. But you also have done, this is in computer science, data structures, courses, etc. But you also have life on internet, and you know that, for example, you can try to improve a particular picture by running some sharpening algorithm. And if it is taking, if you spend more time, it gets more and more sharp. Those are things where if you stop them in the middle, it's not like you get junk back. Essentially, there is some idea of quality of the result improving, hopefully, as the time goes on. As against the normal computer science algorithms where quality of the result is 0 until the time it terminates, at which point it becomes whatever the quality of the results are supposed to be. Intelligent agents need anytime computational algorithms because they may be asked to make a decision. You can't just say, no, I'm thinking, give me some more time. No, this is the time you have. And you should have thought about what your safety is if I stop you. This is the same thing in the exams, right? I mean, there's like end of the exam. And you basically can't say, the stuff that I know, I will do it at the end. The stuff I don't know, let me start working on it in the beginning. And then you spend the entire exam time, then I say the time is over. I say, oh no, there's like 5 questions that I knew the answers to, and I never wrote them. Well, that was a bad policy. You should have written the answers to the questions that you know the answers to, because it's a limited time exam. But those of you who are in this class, I assume that you know this policy already, because you wouldn't have passed through the limited time exams if you kept all the easy questions to the end and worked on the hard questions in the beginning, because you may not be done with the hard questions. By the way, it took me a long time to figure out that some people actually in US, when I became a teacher, first I realized that people have this idea that the exam paper is set in such a way that the questions in the beginning are easy and the questions on the last page are hard. And so I have to keep telling people that, here's the exam. If it's a limited time exam, then I say, first look at the entire exam before you start working on it. And nobody would do it because they have grown up with the GRE, Educational Testing Service folks, who said, we want to make your life easy by putting the questions in approximate order of difficulty. The world doesn't have to do that for you. In fact, if there are like 5 topics and there are 5 questions, it could very well be that depending on your background, like the 5th question is the easiest and the first question is the hardest. You should have checked how to spend your deliberation time. This is all about anytime computation, and in fact, depth limited Minmax is doing anytime computation. Of course, the only difference is that there are all sorts of interesting things. If you read the textbook, I won't have probably time for doing all that, but one of the interesting things is depth limited Minmax has all sorts of issues such as horizon effect. I'll take a lovely example of horizon effect. It is the following. Everybody uses this. Situate yourself in 1939. I think the Second World War started in 39. Okay. And so the allies, quote unquote allies, are playing this zero-sum game with Hitler, right? And Hitler says, I'm going to take Poland. And now you have to say, okay, let him take Poland. After that, he'll get sick of doing war. Versus, let's declare a war. You understand what I'm saying? Now, and then, of course, then they will take Czechoslovakia, then take something else, then take Russia, etc., etc. The problem is, if you have the full search tree in front of you and you simulate it with perfect information what Hitler is going to do, then you would have realized that it's much simpler to actually start the war in 1939. You see what I'm saying? But on the other hand, we all, in real life, do depth limited look ahead. We do limited look ahead. When we do limited look ahead, sometimes the inevitable can be pushed over the horizon. There's a name for this, kicking the can down the road. You see what I'm saying? And so online decision making is what got us Second World War. First you give the Poland, then he starts taking Czechoslovakia. Okay, I'm pretty sure after Poland, Czechoslovakia, he'll be sick of their food and he'll stop going on wars and he'll just go back to Germany. But this will never end. At some point of time, he's about to take England. Then I say, yeah, maybe it's a good time to start war. Now you might say, why can't we just right away start war? Because maybe he would actually have stopped, depending on your opponent. If you looked at the full tree, you would have known whether they are likely to stop or not. But since you're looking at the partial tree, with limited look ahead, you will make inoptimal decisions, suboptimal decisions. This is something that we just have to live with. Do you guys understand that? Limited look ahead is the only thing we can do, and we will do suboptimal decisions, except in extremely few cases. So I'll get to you in a minute. In fact, in computer science, there are these things called greedy algorithms. If a problem, if the greedy algorithm winds up giving an optimal solution, that's the kind of problem that anybody with half a brain would have been able to solve. It's not a hard problem. Do you understand what I'm saying? So greedy algorithms normally give you pretty suboptimal solutions. But there are some problems that are so easy that greedy algorithm already gives them the optimal solution. Most of the time, you don't expect greedy algorithms to do well. Those are the kinds of problems where online algorithms will do extremely well. Because online is basically limited look ahead, greedy decision making. Question, yes.
Earlier you mentioned that limited or like depth limited.
Min-max.
Yeah, I think something like that. I forgot the exact words, but you mentioned that it only serves to delay the event. This sounds like a strange question in my head, but how exactly can you determine what is inevitable and what isn't?
That's my point. That again, the interesting thing is it's actually, so the understanding horizon effect is actually quite tricky. If you don't know, so if in fact you cannot completely predict what Hitler may be doing, then basically all bets are off, because even if you had a complete min-max tree, so the min, under the min, the moves that you put, you should know what your moves are. The moves you put below your opponent, right? You basically are assuming what moves they are likely to have. You're assuming it is a perfect information game. It turns out nuclear bomb during Second World War is an unknown option. Japanese didn't know, for example. So even if they were doing complete min-max search, they would never have realized that you might actually have this extra option, the secret option. Remember that we are looking at perfect information games where there is no secret move. It almost looks as if chess is something that any random person should be able to play because there is nothing unknown. The interesting part is even with everything known, it can be computationally extremely costly. And then on top of it, if you don't know some of the moves, or if you can't see, so if you can't actually see the board, that will be blitzkrieg, which is like blindfolded chess, it will be harder. If you also don't know, at least in blitzkrieg, you know all the moves that your opponent can make. You're playing blitzkrieg, where the opponent can also get like a firebomb and start throwing it at you. That's a completely new thing. It was like you didn't expect this to be part of the game. Do you see what I'm saying? So the horizon effect that I'm talking about is if you actually have the complete tree, and if you actually did the min-max, you would have got the optimal policy, even then the depth limited one will not give it to you because the depth limited one is likely to essentially push the inevitable because you are using the evaluation functions, and those are imperfect. Yes?
This reminded me of how some of us in the stock market, where you have a stock and it keeps going down.
Pay attention to this guy, he has money. Yeah, okay, go ahead.
It keeps going down, and you keep thinking that, yeah, I'm not going to sell it now, I'm going to sell it later on. Or I'm going to buy more later on.
That's actually, stock market is slightly different. If you think stock market is a complete perfect information game, you should come up more often to my office and tell me how to do this. Because I'm not doing well. Right?
Can you use something like Minmax to solve, to put it to use in stock?
Yeah, you can. People do. But the point is then the guarantees are off. So you can apply min-max in a world which is what is called open world. Open world basically means imperfect information about even the moves of the opponent. You can apply it acting as if what you know is all that is there. But then there's no guarantee that even if you did the complete min-max, you would be optimal. At least here, complete min-max would be optimal. The only reason you couldn't be optimal is because it's just too costly computationally to do complete min-max. So you're doing look ahead because you can't do the full computation. It turns out that the same idea will wind up working if in fact the world is much worse. That is, it's not even perfect information. And there's not much of a guarantee here anyway, other than for the full tree. There, the full tree doesn't exist. Again, this is the kind of thing I'm saying, this is not an exam question. But you have to understand how these things connect to each other. You see, why are you going from A-star search to min-max to suddenly talking about MDPs? Okay, it's like mind is what you need to change your mindset about thinking about algorithms. Okay, so yeah, so all this stuff I already said, depth cutoff and online search. And online search is not guaranteed to be optimal. Agent may not even survive unless the world is a good. But you can say, I don't want to do online search, I want to do offline search, but then you might have that possibility if there is no time pressure. That means the world is not dynamic. In some sense, when the world is static, that means there's no time pressure. Because things change only when you move. The world in which you are in, even if there is nobody else in this world, it is, strictly speaking, not static. Why? Because unless Jeff Bezos figures out how people can live infinitely long, you understand? If you take more than about 100 years, then you would be dead. So the time is going on. I mean, you yourself, the processes in your body are continuing. And you're becoming older and older. Some of us faster than others, but they're becoming older. So really, the world that we live in is never really static. At least the people live in. We have time pressures. Even if we are the only person in the world. Mind-bending. Yes, go ahead.
Is there like some way to find like, not only say like an optimal time, but like a time that gives you a good enough result for like anything with like a time limited?
So one of the interesting things, I mean, we'll talk a little about that in Monte Carlo research, for example. And one of the interesting things is you might be able to put bounds sometimes on, what you can do, what guarantee you can do if you give this much time. But more often than not really. It's very frustrating. I mean, you're coming out of data structures and algorithms courses where you want to prove determination and optimality. But in the real world, yeah, I mean, you can be optimal, but you take too long, so the world is not going to wait for you. Okay? So, by the way, one very strange thing is everything is connected to everything, and in this course, and especially the way I would teach you. It's not like, algorithms come with non-porous boundaries. Okay, so the ideas don't come with non-porous boundaries. So if you could do depth-limited min-max, when you actually have an opponent, which is what you're doing, why can't I do the same idea for A star? I know that A star was supposed to be for static worlds, but we kind of sort of know that there is such thing as static area. Everybody has patience limitations. So you started the A star algorithm, it is taking forever. You want to know, okay, at least let me do the first step, man. If you're doing the Pac-Man thing or whatever, right? You do the first step. Do you see what I'm saying? So A star says, no, I won't tell you the first step until I reach the optimal goal. Greedy thing will allow you to do it. For example, the greedy search would be, if you have G value, so basically at any given node, if you are at this level start node, and there are, let's say, A, B, C are the moves you can make, you can compute, that let's say this is 4, this is 5, this is 7. So to get to A, the G value is 4, G value here is 5, G value here is 7. Notice I'm talking about G now. I'm not like talking about evaluation function, I'm talking about G's and H's. Okay, right? And imagine for ABC, remember, if you're A star, you would have had a heuristic that's waiting for you. That's sort of like your evaluation function. Actually, it has better guarantees. So if it turns out that H is, for this is 3, H for this is 1, H for this is maybe 5, then the F value would be 7 here, F value will be 6 here, F value here will be 12. So I have 3 moves I can make, with just one step look ahead, I realize that this guy's F value is 7, this is 6, this is 12, which will I pick? If this is the only information I have. B, because A star always picks the lowest F value. A star always picks the lowest F value. Do you see what I'm saying? If I can do this, why do I do A star search? Like, why did you waste your time figuring out optimally, etc., if I'm allowing you to do this? I would argue that this is exactly what you were doing when you just did one level, depth limited min-max. And you said, wow, I'm decided that the middle move is the best move. It turns out that was also middle move was the best move. But then you had more time. So you expanded the tree and you figured out what's the better move. You have more time, you expanded the tree, you figure out more what's the better move. Why can't you do that for a star search? You understand what I'm saying? A star search tree would be even smaller because there is no min. It's just you and your computational limitations. Okay? So this is basically greedy. And to get some sort of a depth limited version of A star search, you would do basically huge animation. So if I'm here at this point, f equal to 3, f equal to 3, it looks like both of them are as good after the first level. So I'll pick one of them randomly and I say that's my fallback. But then I'll continue expanding nodes. By the way, the nodes that are being expanded here are from this real world grid where I am at the start node S here. I can either go this way or this way. And if I, there's N and there's M. And from N, it turns out basically, so from N and M, from M basically, if I'm only going forward, if I'm not allowing back moves, essentially let's say, there is nowhere I can go, and I'm stuck. Because of the real world. So its children are empty set. Whereas for the M, there is K. So now I will compute the F values for the leaf level nodes. Back them up. And figure out which of the children is leading to the lowest F value at the leaf level. And that's the move I will make. That's exactly what you did in Minmax search. You see what I'm saying? This is what is called real-time A star search. And real-time A star search will not have the kind of guarantees A star search will have unless you go fully through the lowest level of the tree. But it is likely to have higher performance, better performance in terms of quality of the solutions it reaches compared to the purely one-step greedy A star search. So what I'm saying is, before it was all or nothing computation. Either you start the A star search and wait until it comes back, or basically just do random stuff. Now I'm saying, I'll figure out after one step look ahead, I'll figure out what's my best step. I'm about to make it until I'm forced to actually make it. So I keep it as, okay, that's my safe fallback. Then since more time is there, I'll continue expanding the tree. You see what I'm saying? There's no real difference between what I did in RTA star and depth limited min-max. It's just the names are different, the settings are different. They're both online algorithms. Okay? Questions? Yeah.
I'm wondering what the difference between like a heuristic function and an evaluation function would be.
Very good question. Very good question. The answer is that for the case of heuristic functions, you actually have this notion of the cost to the goal, optimal cost to the goal, and trying to make sure that the heuristic you have is a lower bound on that cost. And if it is lower bound, then you will wind up having useful properties such as optimality if you do search with that. And in fact, even RTA star with admissible heuristics has better properties. For example, one of the things RTA star can do with admissible heuristics is it will at least be complete. That means if there's a goal, it will find it eventually. Okay? Evaluation functions, on the other hand, anything is an evaluation function. It's a very, very good question. It's anything is an evaluation function. That's what I feel like. This is as good as this. And that's why I said the domain experts will come up with, well, I think, how do you give a value to the current board? Well, I'll say, I have this fake theory about how chess goes. And the fake theory basically says the positional strength of the queen and some positional strength of the knights, etc., they have to be added, subtracted from something else, and I get a magic number. And that's my theory, and I'll stick to it. That theory might be better than your theory of all boards are created equal. But it has no guarantees. It's a very, very good question. Again, the same idea can be applied in many different settings, but whether or not proofs will go through depends on some additional assumptions. There is no such thing as, so here is a very interesting question. What is min-max actually? When I said min-max is complete, what exactly did I say? What was the proof I'm giving? That a min-max, perfect min-max agent, here are two ideas. One is a perfect min-max agent will win in the least number of steps, assuming all steps are equal cost. That's one idea. The other idea is the perfect min-max agent will lose the least number of times if you play the game in, million times. Do you see this? These are two very different guarantees. What did you think the guarantee was? The person at the very end of the class, hello? What is the guarantee? This is why you should be paying attention instead of looking at your laptops. And I don't have to tell this to one set here and one set you. Please follow. So what guarantee? Do people understand what I just said? You might very well have thought it's the first one because A star search says the least cost path. Min-max actually, in fact, the funny thing, here is the funny thing. Min-max assumes a perfectly rational opponent. And what it is trying to do is minimize your loss probability. If you ever wind up playing chess with your 2-year-old nephew or niece, and you feel like doing complete min-max search, then don't be surprised if all of us stand around you and laugh at you. Do you understand what I'm saying? Yes, you won't lose, but what a bozo. Your opponent doesn't even know the difference between a candy and a chess piece. And you're trying to say, let me not lose the game, let me do the perfect, min-max search. The guarantees are very, very different. All min-max is doing is min-max is risk averse. It just makes sure that you don't lose, even in the perfect case. Okay? One other very interesting thing that I won't go into too much detail, but it's worth thinking about, is this idea, look ahead is better. Right? The deeper you go, the better the decision is. In the depth min-max, an agent which looks 4-ply is better than an agent which only looks 3-ply. This is our general assumption. Right? But why is that true? Kind of intuitively it looks like they thought more. But the point is that one of the funny things in real world is if you don't go all the way to the end, in fact, your estimate of the future may non-monotonically change. It's not that it will monotonically improve. It will actually change non-monotonically. So a guy doing a 3-ply could, in the worst case, in some cases, do actually better than a guy who's doing the 4-ply. By that argument. And in fact, a guy called Dana Now, who was on my PhD committee gazillion years back, came up with games called pathological games. Pathological games where going deeper worsens your performance. And yet it doesn't seem to happen in any real games that people have been playing. Why? It turns out that the reason is in most real games and real world situations, success is elusive. Death is everywhere. That's a very optimistic way of looking at it, right? I mean, suppose all of you are here because you want to get like the Turing Award or Nobel Prize or something. It's not at all clear to me what steps you have to do to make sure that you'll get the Nobel Prize or Turing Award. If you get run over by a truck on the Mill Avenue, zero chance that you will get the Nobel Prize or Turing Award. Because actually neither of them are given posthumously, it turns out. It's one of those things. You see what I'm saying? So failures are actually shallow. In many reasonable search trees, there are shallow terminal nodes that are extremely bad for max. If there is a reasonable percentage of them sprinkled throughout the search space, then you can show theoretically that an agent which goes deeper can never do worse than the agent, probabilistically speaking, than the agent which tries to make things shallow. Do you guys understand that? Again, these are things that you can just take it, makes sense. I mean, deeper is better, but deeper doesn't have to be better. And the reason deeper is better is because we live in worlds where failure is everywhere, success is elusive, based on whatever definition of success you have. And in those worlds, going deeper, it tells you the traps. Basically, being run over by a truck on mill is a trap for your life because you can't come out of it. You avoid traps, then you might actually live to be able to. And so by going deeper, looking ahead, you will at least look at the traps. Yes, go ahead.
I was going to ask you how to look at the example of pathological game because it's really hard to wrap my mind.
Which one, the game tree pathology?
You have an example of pathological game?
This one, yeah, you have to look at his paper. Yeah, send me a message, I'll show you this. Again, basically any game where there are no failures at all, imagine. Then going deeper doesn't have to happen. Okay? And actually, surprisingly enough, Go, which I don't understand. I understand even less of Go than chess. Go actually has very few traps, quote unquote, compared to chess, as I understand. Okay? Okay, so this was the thing that we were looking at last class, right? And then we basically said between Go and chess, chess went with search, and Go originally went with search, and it used Monte Carlo tree search, but then later on it also tried to learn better heuristic evaluation functions by massive playing. Okay, now it turns out that one thing that we talked about here is the Monte Carlo research that we did not explain what it is. And I want to explain that to you. Because that has yet another very interesting property. One of the funny things, as we go forward, you'll find that Monte Carlo tree search algorithm. So if you want to write lines of code, writing the full A-star search algorithm takes a large number of lines of code. Okay? Writing RTA star, much fewer lines of code. Writing greedy A-star search, obviously fewer lines of code. This is basically what's called a sampling-based search, which we'll discuss in a minute. That will take even fewer lines of code. It's just that you do multiple probes into the search tree. I'll explain to you that in a minute. Each probe is cheap. You do many of them randomly. And then you get a sense of how good stuff is below this tree, below this node. So all the action is actually doing the same thing many times as against writing a complex piece of code. So the algorithms for sampling-based ideas are easier to write, but proving any properties on them is much harder because that requires sophistication in how, like, basically sampling works. Okay? So that's what we're going to do. So basically, the reason you want to think about Monte Carlo, it turns out, is the idea that I had for making things online, depth-limited min-max, that is still too costly sometimes. Because what you're reducing is the depth, but you're not changing the breadth, branching factor. And it turns out that for chess, branching factor is what, about 35? And for Go, the branching factor is 361. So you would always be doing much less deeper tree if you have to do the full tree at a time. Okay? So instead, and the other thing is that depth-limited min-max search basically is asking you to tell it how good is the middle node. Right? For example, I need to know how good is the value of these nodes. The rules of the game don't tell you how good those nodes are. So you come up with these hocus-pocus evaluation functions, which we just discussed, are basically made out of thin air. Now it turns out that for chess, at least, people had a reasonable idea of how to make these evaluation functions. For Go, it was extremely hard because actually, again, this is one of these places where, how many of you have actually ever played Go? Okay, so you would understand what I'm saying, which is that things like chess, basically, the game position, two game positions might look almost the same, except in one position, basically, your king is under attack, and the other position, everybody else is in the same place except the king is not under attack. And most of the pieces are in the same position, but except the king is not under attack. These two game boards are completely different in value. There can be fatal decisions, fatal configurations in chess. Go, on the other hand, I understand based on what I read, and I think this guy can tell you, things are in flux up until the end. And it's extremely hard to tell a good board from a bad board in the middle place. So evaluation functions for Go, they tried them, they just didn't go anywhere. So when Go finally, when we started making an improvement in Go, the AlphaGo wound up, by the time of AlphaGo, basically people realized that one of the things they have to do is get out of depth-limited min-max search because it expects the evaluation function, it expects the full depth at a time, more or less. So instead, they came up with this idea, this again, that existed across many different areas. We'll talk about it here first, we'll talk about it many times later on, called Monte Carlo tree search. The idea is extremely simple. The idea is actually extremely simple. In fact, there's only one interesting part in it, which is the backup. Even that is not that particularly hard. I'll tell you how to do that. The interesting part is how to prove that it does anything reasonable, which we will skip. Okay? So instead of depth limited cutoff, we can estimate the goodness of the nodes by playout. So if I have a node here, right? So if I have a node like this, before, to understand how good it is, I had to sort of make a tree below it at some depth, find the evaluation values at the bottom, back it up by min-max. And this tree can be fat if the branching factor is high. And the evaluation functions can be bad for some games. So what you do instead what you do is you basically, if you're looking at how good this node is, I will make random moves for me, my opponent, for me, for my opponent, for me, for my opponent, until I hit a terminal position. Do you understand what I'm saying? It's not infinite depth tree, so you will hit a terminal position. When you hit the terminal position, for making life simple, we'll assume this is a binary game. There is no middle value, either win or loss. That's a very reasonable game. Chess is also that way, right? You don't get like middle points. It's either win, loss, or draw. So in fact, when I gave evaluation function values like 14 and 15 for a chessboard, what the heck do I mean? There's only plus infinity for win, minus infinity for 0, and 0 for draw. And minus infinity for loss and 0 for draw. That's the only numbers that actually make sense. Everything else, I'm just hoping they make sense with the algorithm because it's taking mins and maxes over real numbers. Here, on the other hand, I'll go all the way to a leaf node, and I'll check whether the leaf node is a win for the max or not. And all the way to the terminal node, and I'll check if the terminal node is a max or a min. You have to keep making random moves for you and your opponent until you reach a terminal node. So terminal node is basically any goal node has to be connected to terminal. Okay? Any goal nodes are basically terminal. So the idea of being goal here is you need to reach the terminal node and check whether it's a win or a loss based on the rules of the game. Okay? Right? And when I do that, I have this, basically if I do this a bunch of times under this node, and every time I seem to be winning, then maybe it's a good node. That's the basic idea. Except I can basically make it into an algorithm. I'll just show you in a minute how. That is Monte Carlo tree search. Here, at some point of time in the middle, in the beginning, you'll only have the start node. In the beginning, you start with just, Max starts with the empty board or his current position. And then assumes, basically, and she keeps the win to the win ratio. That means how many times have I come to this node, and how many times while I was passing through this node, I ended up in a win. If it is mostly leading to wins, then it's an auspicious node. If it is mostly leading to losses, it's a bad node. So I keep track of the win ratio. Not a bad thing to do. And if I'm keeping track of it, as at some point in the middle of the game, I might have a tree like this. So basically, you slowly started letting new nodes in, and I'll tell you how the new nodes come. But at some point of time, you'll have a tree like this, where this node says, I totally played, because it's the root node, that means I have played 100 rollouts, 100 playouts. And of the 100 times, it ended 37 times they ended in wins. The other times they were losses. Now it also turns out that this guy has these as the children, according to the piece of the tree that I have seen. And those guys basically share, below this. Now notice that because it's a min-max tree, this is a max guy, right? So this guy has 60, this is 1, and this is 2 wins. And remember when max loses, min 1. Right? So if you add up 60 plus 1 plus 2, you get 63. 63 plus 37 is 100. So apparently in this case, they didn't have any draws. Right? So you can imagine that you will have a tree like this. So at this point, basically I'm at this node, and I'm trying to see which move should I make? Which move should I make? Right? Just like in A-star search, I would say, hey, this seems to like a pretty losing road, because 60 out of 79 times, my opponent wins, that means I lose. You see what I'm saying? And similarly, 1 out of 10 here and 2 out of 11 here. Right? And so if actually, in fact, this is already an intermediate state, but in the beginning when you had only those 3 states, you would have just taken whatever is the win ratio for the node at that point of time and pick the node that has the best win ratio for you and say, that's my move. But I say you have more time, think more. So think more is got you here. You are in this tree now. So if I say you still have more time, think more. Then I'll say, pick one of the leaf nodes. Pick a leaf node, a terminal node. And the minimum, some simple idea is the greedy pick. Pick the one that's like the best among the leaf nodes. And then do extra probing below it. And see if you can improve its valuation. And if so, then you propagate those valuations higher up. This is basically you're exploring the tree little more. And it's a much more fine-grained exploration of the tree than what depth-limited min-max does. Okay, yes, go ahead.
All right, I got lost in does the number represent the ratio of wins to the amount of times that I've noticed?
No, not time, the total number of rollouts. That means basically what we'll do is under any given tree, you might actually have every line of play. So the real world essentially has no search. Right? The real world, if I look at an actual specific game between Kasparov and either a machine or a human, you'll say, first Kasparov made this move, then the other guy made this move, then the Kasparov made this move, then the other guy made this move, and this move, and then the game ended. That's a rollout. In Queen's Gambit, when you show the games, you just basically have to show the path that they followed. That's it. They thought about a lot more possibilities, but they actually followed that path. In the back, when you see it afterwards, that's the path they followed. That's called a rollout. The question is, how many of the rollouts going through a board configuration ended up in win for the max versus loss for the max? That's what that particular ratio is telling you. And for the same thing for min also, for the rollout going through the min's node, how many times has it become a win for the min and loss for the min? Okay? So then the next thing I need to do is so it turns out that of all these things, assume that I decided to expand this node. It turns out picking the node to expand is actually one of the $1 million questions. We'll assume that one reasonable idea is to be greedy. So pick the most promising descendant and see if you can get a better idea as to their valuation. Notice that these things can also be thought of, these win ratios can also be thought of loosely as probabilities that you will win if you went through this node. Right? So anyway, turns out that I am in this place, okay, and then I basically for 27 to 35, I have to pick H height. So the game tells me how many children this guy has. Maybe, if it is Go, it would have had 361 children on the average. I picked one of them. You see what I'm saying? I picked one of them. And then from that node, at that point, that node has 0 by 0. Because You never played that node before. This is the first time you saw that configuration. Then I basically do a probe. Starting from that board configuration, I simulate, okay, because this is, notice that the purple is max for us, and whatever this other color is min. Okay, so essentially I have this max node. Below this, I then make a min move. I mean, I simulate. Let's say min makes a move, then max makes a move, then min makes a move, then max makes a move. Randomly pick, just randomly. I know that that's not how people work, but randomly pick until you reach a state which is either definite win or a definite loss or a definite win. Imagine that in this particular case, it turns out black wins in this particular layout. I didn't show you, but in this layout that I played in my head, black is winning. That means min is winning. That means max is losing. So you learn something little more about this tree, about this guy. The next part, which is actually the only interesting part of the algorithm, is how to propagate this knowledge through these ratios. Notice that now we have done not 100, but 101 total plays. So everybody will get a little bigger. Everybody on the path to this node will get a bigger denominator, but their numerator will either increase if they're a max node. I'm sorry, if there's a min node, because this is actually a fail for max, or remain the same if it is a max node. That's exactly what happens. Just give me a second. Let me show you this. Okay, so this has become 0, 1, because this poor guy, if this was where max was and you just did one rollout, and that one rollout, basically the dice were stacked against you, you lost. So I said, I tried once, I failed. So 0 out of 1 is my ratio currently. And then because this guy is 0 out of 1, its min guy, we used to be 35, becomes 36 games, and used to have 27, now one wins 28. Is this like calculus? This is just adding counters. Okay, and then I'll cut to you. Continue, and this 28 here, when you come here, this used to be 53, becomes 54 now, because there are more games. Before the numerator was 16, it still remains 16, because the new one is a loss, not a win. And then continue here, used to be 79, becomes 80, used to be 60, becomes 61. Continue here, used to be 100, becomes 101, used to be 37, remains 37. Do people understand this? This is what you do if you do one probe. I can ask you to do one more probe, so you'll pick one more node and probe, and then do this again. I'll say some more time, you do one more of this. I'll say some more time, you do one more of this. Before, if I give you extra few seconds in depth limited min-max search, you say, I'm sorry, the next amount of time I need is about 3 days. Because I have gone up to like 4 ply. When I expand the depth to the 5 ply, the tree increases exponentially. So if you give me 3 more seconds, it's useless. Do you see what I'm saying? Whereas here, a few seconds here, a few seconds there, I can use all the time I can. Because a rollout is considerably cheaper than a full tree below any node, a full depth limited tree below any node. Yes, question. There was a question.
Yeah, so I was going to ask, what happens if the opponent chooses suboptimal node?
What?
What happens if the opponent chooses somewhere you didn't expand on the?
No, but notice that these are only probabilities. These are only probabilities. In fact, remember that depth limited min-max search might have been wrong anyway because of the evaluation function being wrong or the depth being too small. The only thing we are saying is asymptotically, both depth limited min-max and Monte Carlo will improve their performance if you give them more time. Except Monte Carlo can take time in the increments of minutes. Depth limited min-max will start taking time in the increments of increasing increments, like first a couple of minutes, then a couple of days, then a couple of years, then a couple of whatever. Because as you keep increasing the depth of the tree, the next amount of time you have to search would be humongously higher. So this is just a great idea because you never get, it's like saying, either give me, if I say I'll have extra time for your exam, you should take it. If you say, no, I'm sorry, the way I think, after 1 hour, the only amount of extra time I can take is 2 more hours. And after 3 hours, the only amount of extra time I can take is a full day. Right? Then basically extra time I'm giving you is wasted for you. That's why Monte Carlo research is great. Everything is fine and dandy. It's like one of the greatest ideas. And it's like, why, by the way, why people call it Monte Carlo?
Monte Carlo simulations.
What is the Monte Carlo?
Random simulation.
I understand. Why call it Monte Carlo?
You perform.
What?
If you want to find the probability of something, if you do it a lot of times, that's something.
Where is the name Monte Carlo coming from? What? It's a casino. Where? Where is it? It's a casino where? Monaco. You guys have to keep attention to things outside of computer science. The reason you keep talking about Monte Carlo algorithms is because Monte Carlo is a casino. And in casino, it's a sampling. So there are Las Vegas algorithms too. It's just that the Europeans got the dip, so most of the sampling-based algorithms are Monte Carlo algorithms. If you don't know this, and if you keep telling people, it's because it's probability, they'll look at you saying, what kind of a dweeb are you? Have you ever gone to a casino? I didn't go to a casino. I hate casinos, but I should know where the names are coming from. Remember, the entire theory of probability was invented for casinos. See what I'm saying? And then people used it everywhere else. So that's the reason of the Monte Carlo thing. Saving the very last for the best. And before you leave. Which is, I kind of said you have to pick the select a node at the leaf node to expand. The question is, which node should I expand? The simplest idea is to pick the greedily best node. That is the one with the best win ratio from the perspective of the guy doing the expansion. So if Max is doing the expansion, pick the one that has the best max win ratio or the lowest min win ratio. This is a great idea. Why won't it work? Yes?
It's almost like a confirmation bias, kind of, like if you're only exploring one node, then there might be a lot.
It's basically what it's, so what he's saying is that unlike depth limited min-max, where the entire breadth of the tree was looked at every level. That means you considered all your options at every level, whether you like them or not. You just consider it for a shorter depth. Here, you are only considering the options that you are selecting. If you select the things that work well because they worked well before, then there could be parts of the search tree that you have never selected, and they have gold. They have nirvana. They have whatever you consider is the best thing that can happen to you. So what you need to do is don't just select based on the win ratio, but also give a little push to the underexplored directions. Underexplored directions should be given a little push. That's what this guy is saying. This complex formula, essentially the intuition about this formula is, this is the win ratio, and this is the level of underexploration. And what it's saying is the log of the number of times the parent was expanded, that means parent, you went to the parent, divided by the log, by the number of times this particular child has gone. So if you have a parent that have looked at huge number of their children, but have ignored this one loser child, without checking whether loser are actually Jesus, you should select it once. What if it's Jesus? Until you select, you won't know. You see what I'm saying? Why is this formula the best formula? The intuition behind the formula you should understand. Because this corresponds to one of the biggest trade-offs we have in life, which is what is called exploration versus exploitation trade-off. I mean, after you're done with elementary school, you got a bunch of ideas about how the world works. Time to start making some money. Use the knowledge. Some of your folks probably dropped out after elementary school, and they're making money. You chose to explore a little bit more, went to high school. And some of you then continued to explore a little bit more, went to college. Some of them, like this guy, continued after the college. How much exploration is good? Zero exploration, very bad. If you always explore, your parents will start looking at you, or your significant others will start looking at you saying, settle down already. You are like 99 and a half, how long do you think you will live? You see what I'm saying? That's what this particular formula is capturing. It's one of these great ideas that you'll keep seeing. This becomes important in reinforcement learning too. This is where they say, sometimes try things, sometimes take the turn that you haven't taken. So if you keep on following the same path to home, in a world where you don't know the full map, you might be missing a path where they're giving away free candy. Until you go there, you won't find it. Of course, then you will explore, then you'll find they're not actually giving a free candy, they're hitting you with big bats. So if you survive, you'll say, next time I'm not going to go that direction, I'll stick to my old direction. But without exploration, you won't have known it. So Monte Carlo research works the way I explained, except when it selects not the greedy way in terms of what is the most winning node, but the node that is a combination that's selected based on how winning it is and how underexplored it is. So the nodes that have been underexplored before. So think of this as affirmative action. And I say it in the best way possible. Because the nodes that you have not seen, if they can actually do extremely well, you're doing yourself a disservice by not seeing them. So you can say, oh, no, this is not good, this is affirmative action. I should only look at the win ratios. But that's just basically the knowledge that part of the tree you see till now. Think about this. We'll stop here. Next time when we come back, we will start talking about markoutation processes.
Please sign this attendance sheet, whosoever has not signed this yet. So most of you guys have just written the date again, I don't know why. So just check if you have not signed this, because I don't need the date, of course. Yeah, I guess a couple of people just wrote and then everyone followed it. Just please make sure of that. No, just make a signature. Use the don't come as a